Okay, as we continue in chapter 2.1 about limits of functions, we're going to get to another example. This one is taking the function f defined to be x squared minus 9 over x minus 3. And I guess it's worth stating right now, what's the domain of this function? Oh, say it again? Yeah, all real numbers except for 3. So I'll just make a note. I'll put capital D sub f for the domain. It's all real numbers except for the number 3. And this is a nice function in that now that we know that, we can simplify it. So we can say, notice that x squared minus 9 over x minus 3 is x plus 3, x minus 3 over x minus 3, because this is the difference of two perfect squares on the numerator. So it turns out to be just x minus 3, with the caveat, though, this function by itself is... Sorry, I canceled out the x minuses, so yeah, thank you. Thank you. This function by itself, f of x equals x plus 3, has domain all real numbers, but this is where we obtain the domain. So we can simplify that to just say, we could simply have said, or we could say it right now, f of x is equal to x plus 3, but it's not defined at the number x equals 3. It's not in the domain. So if we're to graph this, it would have a hole in the graph at the number 3, it would have a hole in the graph. But the limit exists, and we might be able to guess what the limit is. Just fill in that hole in the graph, kind of make it a continuous function, and we know exactly what that limit is. Because remember, when we want to prove that the limit exists, we have to know what the limit is in order to prove that, using the definition. So we've got this linear, I'll call it a line if you graph it, except for that one little point. And so what do we suspect that the limit is? That the limit as x goes to 3 of f of x is what? Just plug it in and you'll get a 6, right? Remember, f of 3 does not exist, but if we were to fill that hole in the graph, it'd be the number 6. All right, well, here's how we look at the proof. Just as any time that we're going to prove a limit, we need to start off with an arbitrarily chosen epsilon. Let epsilon greater than 0, or let epsilon be greater than 0 be given. And we will find a delta that's greater than 0, such that the following holds true. This is just using the definition. If 0 is less than x minus 3 is less than delta. And what is that? Another way of saying that is, for any x that is within delta of the number 3, it's close to the number 3, but not equal to the number 3. That implies that f of x minus 6 is less than epsilon. Again, all we've done here is use the definition of what it means to have a limit at a certain point. And we know what f of x is. So I'm going to put a little bit of we could really finish this proof up in one or two more sentences. I'm going to put a little bit of scratch paper here. I'll even call it scratch paper. Notice that f of x minus 6, we know is x squared minus 9 over x minus 3 minus 6. And we're going to need this to be less than that arbitrarily chosen epsilon. So I'm just doing the scratch paper so we can figure out what value of delta will work for us. So let's just do a little bit of algebra and simplify this. And we would get x minus 3. Just get a common denominator, I'll let you do the algebra. So 6 times x minus 3 over x minus 3. So 6x minus 18. Move all that together. You're going to get, factor it, you're going to get an x minus 3. Okay, if you haven't convinced yourself of that, we'll do it after class. Okay, so, again, this is my scratch paper, not necessarily part of the formal proof. So, we need a delta. Actually, we need this to be less than delta, and I need to find the epsilon that will make that work. Okay, so we need, my bad, this is delta. This part comes from here. We need this to imply change this word to have. Sorry about that. We have this. And we need the same thing to be less than epsilon. And why is that? Well, it just turns out that this is the same thing as this. We know this exists, and it turns out after I did this algebra that this simplifies to exactly this. And I need this to be less than delta, given that it's less than epsilon, given that it's less than delta. So we can just choose delta to be epsilon and it's going to work. We have this given to us right here. And what we need is for this to be less than epsilon. We need this. So all we need to do is make our epsilon equal to delta, right? So we have that. I'll just say just choose. We're looking for the delta. Delta equal to epsilon, and it's going to work. So this little scratch paper is kind of going to be my justification for the last sentence or two of the proof. Let delta equal epsilon. If 0 is less than x minus 3, less than delta, just like we have right here, then obviously x minus 3 is less than epsilon, because those two numbers are equal to each other, and that's the end of the proof. Is there any feeling why it worked exactly like this? Why choosing delta to be exactly the same as epsilon and not maybe epsilon over 2 or epsilon over 3 or anything like that? Well, it's because this is our f of x. After it's simplified, that's our f of x. Now it's not defined at the number 3, but the slope of this line is 1. If that slope had been 2 or 3 or 4, then we would have ended up having to change our epsilon accordingly.